Hey, Honors Chemistry, it's April 16th, Thursday. It's good to have you on board. Reaction rate 536. Yesterday, I gave you demonstrations. Actually, I'm wearing the same shirt. It's the same day for me. But anyway, let's go to 536 and breeze through some of these pages so you got the information. It's real important. What is reaction rate? Well, it says right here. It's the change in concentration of the reactants per unit time as a reaction proceeds. And what area of chemistry is this? It's concerned with the reaction rates, the reaction mechanisms. It's called chemical kinetics, sometimes called reaction kinetics. Kinetics means speed. You know, kinetic energy is 1/2 mv, velocity squared. And so it's kinetics means moving along. Okay, it's not, we're not talking about decomposition reactions like when that electrolysis apparatus takes water and breaks it down into hydrogen gas and oxygen gas. We're not talking about that because it's decomposition. When you have reaction rate study, you're talking about studying multiple reactants and how they interact. And as you know, molecules, when they interact, they don't like, let's take these two molecules here. They don't like to come together because surrounded these molecules is a sea of electrons. And we're talking an electron cloud. And so they repel one another as they get close. But then if you have enough kinetic energy, they can smash together. And if you have the right orientation between the molecules, we studied that in the last section, then they might in fact form compound water if they went back in this direction. And so we're talking about multiple reactants and the way they interact. The third thing, along with kinetic energy, might be the frequency. Frequency of what? Frequency of collision. So you have to have the right orientation of the molecules that are colliding, and you have to have the right energy, and therefore you'll have a higher frequency if it's a higher energy of collision. Of course, temperature is simply a indirect measurement of the average kinetic energy of molecules. So if you raise the temperature, you're raising the kinetic energy. The nature of the reactants has something to do with it. If you try to take iron and oxygen and put them together to form iron oxide, this type of iron oxide is called rust. That is a slow process. Okay, but if you were to take a look at the one that we've done so many times, we're taking hydrogen and popping it, that's a fast reaction. And of course, you have to have that energy that we talked about called activation energy. And so in order to make that happen. So the nature of the reactants, are they made out of hydrogen and oxygen? Are they gases? Are they solids? The nature of the reactants, the type they are and that kind of thing, depends upon how fast the reaction will go. Surface area. I showed you yesterday a thing where I took flour, and I usually use lycopodium powder, which is mold spores, moss spores, and they burn real efficiently, and the flame that goes above the pipe is, you know, quite tall, whereas this flame was just a little teeny one, but at least the flour did the job. So if you take and grind up the reactants, there's more surface area. Let me show you that, if you don't mind. You guys know what surface area is all about. I'm going to take a cube. And I'm going to go ahead and say it's 4 centimeters on a side. And so if you want to do the surface area, you've got 4 times 4, that's 16 there. You got 16 there. You got 16 up here. You got 16 on the bottom. You got 16 on the back. You got 16 over there. Got 16 over there. And all of those 16s add up to about 96 square centimeters for surface area. Whoop, not talking volume. But let's suppose we take these little chunks and crush them up. Let's crush them up like this. And so you got that one little square cubic, one little cubic centimeter. And so this is one, that's one, that's one, that's one, that's one, that's one, but there's a whole lot of those ones in there, right? Isn't there? And so it turns out that that is 64 square centimeters times 6. There's 6 of these. And so that would be like 384 square centimeters. When you take it and you break it down into all these little things. And so that's like 4 times. And if you crush it up even more, it's going to just really get a lot of surface area. So you're going to get a lot of exposure to the oxygen of the air and allow that thing to go ahead and burn rapidly. That's why we take a log and we shave it down with our knife before we try to light it on fire. Then we blow, and because some of our oxygen comes right back out in respiration, we get that fire going. And so surface area it depends upon the area of contact. Heterogeneous reactions involve reactions in 2 different phases. Homogeneous, they're all gases or they're all liquids. All the reactants are the same phase or state, and heterogeneous reactions are those that involve different states of matter. There's this thing called catalytic converter that's underneath my car, and it takes metals, and it allows gases to react on the metals. Those would be like heterogeneous reactions. Take a look at the reaction on the bottom of 536, and you see that you got zinc with hydrochloric acid. I demonstrated that yesterday. The zinc is a solid. The hydrochloric acid is dissolved in water. It's hydrogen chloride gas dissolved in water, so it's aqueous, and it forms zinc chloride, which is a solid, and it releases the gas. And so you take a look at these reactants and you say it's heterogeneous. On the top of 537, you're going to see when you crush down coal, sometimes in the mines with the dust, just very little temperature that they have in those mines is enough to spontaneously combust. And unfortunately, you get an explosion in the mine. Sometimes the shaft, the silos, you know, where they do grain and they drop grain off of an elevator down into these silos, and the powder or the grain in there, in the hot summer sun, the grain elevator blows up. And sometimes you see that in the news of Kansas and that kind of thing. Temperature, why does temperature increase? An increase in temperature, why does that increase in most chemical reactions? Well, the reason is because the particles of the reactant move faster. And if they move faster, you get more collisions. The frequency of collision goes up. Then therefore, some of those would give you more, what do we call it? Good orientation. And so therefore, you have good collisions. And it also speeds up the activated complex. Remember the activated complex? That's that activation energy. And what it says is a rule of thumb. I'm on page 537 in the middle of the page. Beginning near room temperature, the reaction rate commonly doubles for every 10 degrees rise in temperature. 10 Celsius or 10 Kelvin, same thing. Concentrations. We talked about, when the zinc went into the hydrochloric acid and I poured more hydrochloric acid in there and increased the concentration, it really reacted much faster. When pilots are coming in for a landing at night, I may have already mentioned this to you, they breathe pure oxygen. Jet pilots get up there in the thin air, and so some of that nitrogen displaces the oxygen. Whatever, it just pushes the nitrogen out of there and allows them to think better, and their eyes work better as well. And you saw that with the experimentation when I had pure oxygen generated from hydrogen peroxide. I broke it down with a catalyst called potassium iodide, and you saw that glowing splint turned into a flame. So homogeneous reaction systems, like gas with gas, that kind of thing, they depend upon the concentration of the reactants. And so on the next page, what we're going to see is 538. And we got collisions and reaction rates. If you have, this is concentration we're talking about. If you have this much concentration, this is reactant 1, this is reactant 2. How many potential collisions can you have? 1. But let's suppose you have a higher concentration of reactant A with reactant B. Now each one of these can react with boom, and that other one can react with boom, and so you got 4 potential collisions. If the concentration of reactant A is tripled and the concentration of reactant B is doubled, then for every one of these up here, you can go boom. This is like combinations, taken 2 at a time, I suppose. You learned that. Okay, and when you count those up, that would be like 6 times the potential frequency of collision. Then we got 4 and 4, and if you count up the number of lines that connect those, it would be 16. So when you got a greater concentration, you have the potential of greater reaction rate. Catalyst is a substance that changes the rate of the chemical reaction without itself being permanently consumed. The action of a catalyst is called catalysis. Say that, catalysis. Okay, and it's an alternative energy pathway. That's what they think. Or they think that they lower down the activation energy. Catalysts cause the activation energy to become diminished. Either that or it's an alternate energy pathway that the reaction can follow as it proceeds. And so the example is hydrogen peroxide breaking down into oxygen and water. And the catalyst that I use was Ki. The catalyst I like to use is manganese dioxide, MnO2. It's a black powder. And you can see a picture of it right there reacting. And the catalyst can be retrieved. That black powder, the manganese dioxide, once the thing turns into water and the oxygen goes away, you can retrieve that black powder out of the water and use it over again if you dry it out. Catalyst that is in the same phase as all the reactants and the products in a reaction system is called a homogeneous catalyst. When its phase is different from the reactants, it's called a heterogeneous. It says metals are often used as a heterogeneous catalyst. And I mentioned that in the catalytic converter under my car, it takes those nasty gases and breaks them down into sweet gases, not quite as harmful to the environment. And so it's the plate that has a lot of holes in it in this little device under your car that is metal. And so it's a heterogeneous catalyst because that's different from the gases that it's catalyzing. And here's a new word. The catalysis of many reactions is promoted by adsorption of reactants on the metal surface. So when those gases hit that metal surface, they are adsorbed, not absorbed, adsorbed. New word for you guys. In our bodies, God made it so that we'd have natural catalysts. Isn't that amazing? Because you have this stuff called enzymes, and enzymes are nothing more than proteins. And then there are vitamins that we might take that work together with the enzymes, and those called coenzymes. But the enzyme is natural and living things. God put it there, and that's because our body produces hydrogen peroxide, and it will harm the cells of your body, unless it's broken down. And so that enzyme in your body can do that, help you to break that hydrogen peroxide down. And then there's the breakdown of lactose by the enzyme lactase. And lactase is produced again by your body. It knows what to do. And if you don't, you're lactose intolerant. The milk sugar gets away from you. And then on page 539 is an example of a comparison of pathways for the decomposition of hydrogen peroxide, H2O2, by various catalysts. Are you looking at that graph on 539? You can see that the very top red curve is uncatalyzed. But then the second curve, the red one there, is chemically catalyzed. And the next one down is enzyme catalyzed. That's like your body producing the enzymes. And then the last one on the very bottom is using manganese dioxide, MnO2, and that will break down hydrogen peroxide even faster, because you can see that those are activation energies, and it lowers down the activation energy considerably from an uncatalyzed process. Okay, so we'll go ahead and talk about concentration tomorrow, page 539. See ya.